All right, so we are starting now chapter 7, which deals with periodic trends. So periodic trends include things like the effective nuclear charge, the atomic radius, ionization energy, and what something is called an electron affinity. So we're also going to briefly discuss metals, nonmetals, and metalloids, but we're really going to concentrate on sections 7.1 through 7.6. So anything beyond that, we're not going to cover in this chapter. Okay, so want to kind of look, we started looking at effective nuclear charge in the sort of introduction video to this chapter, but now I want to look at it with wave functions. So we saw in the previous video that electrons can screen other electrons, just like putting a sheet of paper or a lampshade can screen some light that you see coming from a lamp. Okay, so we also talked about how electrons in lower shells, like for example here the 1s, how these ones are able to screen more effectively than electrons in the same shell. So for example, if we are looking at a valence electron that's in the 2p shell, these 2p electrons are getting screened quite effectively from those lower shell electrons or the 1s electrons. You can see that the electron probability here is they're more probable to be way closer to the nucleus. In fact, it falls off quite dramatically when we get to the most probable location for the s and p electrons here in the second shell. Okay, so these ones are on average closer to the nucleus and they are blocking some of that positive charge. But if we look at 2s and 2p, their peaks are really close to each other in terms of most probable, but the 2s does have this increased peak probability here where the electrons can penetrate closer into the nucleus, therefore screening the 2p. A 2p can screen 2s and 2s can screen 2p. These are sort of overlapping here, but maybe 2s is a little bit better at screening than 2p. Okay, so what sort of the take home from this is that lower shell electrons are going to screen much better. So if we were to say put the 3s and 3p electrons in here, we would see our 3s having the bump, and then our 3p would have a most probable radius probably way out here, okay, peaking out probably around 5 or so. Okay, so then a 3, n equals 3 electron, most of the probability of the n equals 2, and of course the n equals 1 is going to be a lot closer to the nucleus. Okay, so this is important because this is going to lead us to our first approximation here for calculating screening and Slater's law. Okay, so as we work through this, we're going to draw, on our periodic table, different trends. So what this means is we'll be able to draw arrows going left and right and arrows going up and down on our periodic tables to say that as we move across the periodic table, whatever this trend happens to be, effective nuclear charge, ionization energy radius, we can say it increases or decreases as we move up and down. Okay, so we'll come back to this in just a second once we figure out what happens. Okay, so we talked about effective nuclear charge equals Z minus S. Okay, so our first way that we calculate effective nuclear charge is using what's called core electron shielding. So in core electron shielding, we only consider those core electrons to do any significant shielding. Okay, and how this works is essentially one electron in a lower shell is going to block 1 unit of positive charge for an electron in a further shell. Okay, so for example, let's look at a 3p electron in sulfur. Alrighty. Grab our periodic table here. So in order to write or figure this out, we need to know how many electrons are going to shield. So we need a configuration. So we are going to write out the electron configuration for sulfur. Okay, so sulfur, we use our periodic table. The first row. So we have 1s2, second, 2s2. Okay, sulfur's not here yet, so we keep going. 2p6. Okay, we're in our third row now, so 3s2, 3s2, and then sulfur is over here, so we have 1, 2, 3, 4. So 3p4. Okay, so when we are going to do this, we want to make sure we arrange our subshells in order. So we want all the n equals 1s together, all the n equal 2s together, all of the n equals 3 together, 4, 5, and 6. So this will be important when we start dealing with like D electrons and F electrons. We're always going to rewrite our configurations to get all of our n's together. Okay, so we don't have to worry about that right here. So we'll kind of, we can press on from here. Okay, so our reference point is an electron here in this shell. Okay, so we're one of these outermost electrons. So we're saying only electrons closer in are going to block. So what we're looking at is anything with a lower n value. Okay, so we're not going to consider this. This would be considered same shell. This is the same n value, so we're going to ignore those and just look what we have here. Okay, so sulfur has 16 protons in the nucleus. Pilgrim, he says hello. So effective nuclear charge. So we have 16 protons. So that's our Z. And then we have to have our S. So S is going to be the number of electrons that are going to shield. So that's all of these in lower shells. So we have 6, 7, 8, 9, 10. So all 10 of those electrons in those lower shells are going to shield. So that electron here in this 3p subshell is not feeling a plus 16. It's feeling a plus 6. So 10 units of positive charge were essentially shielded by these 10 electrons to give us a plus 6 effective nuclear charge. Okay, so we're going to look at 3s in magnesium. Okay, so again, we're going to do the, we'll write out our configuration, and we have most of it with sulfur. We're just stopping right here at 3s. So this one is 1s2, 2s2, 2p6, 3s2. Okay, so same thing. Magnesium has 12. So Z effective equals 12 minus, so again, these same electrons are going to shield, 6, 7, 8, 9, 10. So minus 10 electrons that are shielding to give us a plus 2. Okay, so we have a plus 2 effective nuclear charge here. All right, so if we go with our trends, we have our first arrow we can put on there, we have our left-right trend. Okay, so we want to figure out a left-right, up-down trend for effective nuclear charge. So we go back up to our periodic table. Okay, so our two that we looked at, magnesium, and we also looked at sulfur. Okay, so we're comparing magnesium and sulfur here. Okay, so we had magnesium with a plus 2 effective nuclear charge, and we had sulfur with a plus 6. So lower effective nuclear charge, higher effective nuclear charge. And if you were to go through and calculate the effective nuclear charge for a lot of these, you would find that it's going to steadily increase as you move from left to right. So in terms of our trends, we can write our first one here. So we have an arrow going from left to right, and we can put that it is increasing effective nuclear charge as we move from left to right on the periodic table. Okay, so that's our trend. So up down, this one is a little bit more subtle, up down. Okay, so it does turn out that effective nuclear charge increases as we move down. Okay, so that's also increasing. effective nuclear charge. Okay, so that one also does. But I made that arrow a lot smaller because it's not as large of an effect here. Okay, so this increase from what we have here, because we are adding more protons into the nucleus, but we're not really changing the electrons that are screening. Okay, so we still have those same core electrons screening for both of these, but the difference is sulfur has 16 protons, only 10 screen, to give it a +6. For magnesium, we have 12 only protons in the nucleus with only the same 10 core electron screening to give us that +2. Okay, so that one makes sense. For up-down, why it increases sort of that way, think of the sort of energy levels for that. Okay, so for this one, for our up-down trend, I'm going to draw just a little tiny sketch here because I didn't leave my, actually we'll draw a nice large sketch. Okay, so let's talk about why it would increase for the up-down. Okay, so recall from chapter 6, we had energy, and we had n equals 1, and then we had a pretty large gap to give us n equals 2, and then n equals 3, oops, that's an n. N equals 3 was a lot closer to n equals 2 than n equals 1 was to n equals 2, and as we move away, we get closer. So on and so forth. Okay, so our distance between shells is getting a lot closer. So they're not doing quite as much screening as we get up here. They're not as effective at screening as we would see down here, where there's definitely, you know, a large difference or gap between energies. So again, because these get so close together, they're not as good at screening. As good at screening. So we do get a slight increase in effective nuclear charge as we move away from the nucleus of the atom. Okay, so again, not a huge effect, so that's why I have the smaller arrow there, but that's why that one is increasing that way. Okay, so the second way that we calculate effective nuclear charge is called Slaters Rule. So Slaters Rule will take into account that in the same electron shell, we do have some screening. So we saw that with our diagram where we looked at the 2s and the 2p compared to the 1s. So Slaters Rule does take into account same shell screening. Okay, so the way we calculate Slaters Rule, we have essentially 4 things. Okay, so kind of our rules. So number 1, if you have electrons in a higher N shell, we don't include that in the screening. There is a chance they can screen, but it's sort of almost essentially non-existent. Number 2, we say if you're an electron in the same shell, so the same N, you would contribute a factor of 0.35. So this is almost like a 35% screening. Okay, so before we were just looking at full screening, but this is just like, oh, you're only going to screen about 35% of that positive charge. Okay, so next, if we go one shell down, so the next shell down, we would have a screening factor of 0.85. So it means they are 85% effective at screening. Okay, so sorry, I had to pause there. So electrons in one N shell lower, again, only screen about 85%. So we give it a value of 0.85. So then all electrons below that sort of one level lower get the full screening of 1. So same shell gets a factor of 0.35. The next shell lower gets 0.85. And then everything below that gets 1. So for example, if we have the nucleus, and let's say we were looking at something, an electron in the N equals 5 shell. This is 4, 3, 2, and 1. Okay, so let's say our electron is right here. Okay, so all other electrons here, so again, this is our electron in reference. So for example, any other electrons that are also in this shell These ones are able to screen this one at a value of 0.35. Okay, so the next one down, n equals 4. So any electrons we had in this shell are going to screen at 0.85. And then everything else below that, so n equals 3, 2, and 1, are going to give a full screening value of 1. Okay, so, excuse me, we get that full screening for 1 there. Okay, so let's recalculate. Let's recalculate what we have for sulfur. Okay, so we're going to take our sulfur, we're going to recalculate what we have. All right, so our electron configuration for sulfur was the, sorry, ran out of here. So 1s2, 2s2, 2p6, 3s2, and 3p4. Okay. So again, we have our 3p electron, so it's one of these. So if our electron in consideration is one of these, that means 3 other electrons are in the p shell that can screen. So we don't want to have a value of 4 here because an electron can't screen itself. So one of those 4 electrons is our essentially electron of reference here. So the other 3 p electrons and then the 2s all in the same shell are going to be able to screen. Okay, so here we're going to get our 0.35 screening. Here we're going to get the 0.85 screening. And here we're going to get the full 1 screening. So what it looks like here for the S now, so S is going to be the 0.35 times 3, 4, 5, so 5 electrons that are screening that way, plus 0.85. So all 6, 7, 8 of these are screening there. And then 2 times 1. Here, we'll kind of box off my little drawing there. Okay, so that is now how we're calculating S. Same shell electron screening a value of 0.35. Next shell down, 0.85. And then all other ones, the 1. Okay, so if we calculate this now, this is 10.55. So now our screening constant is 10.55 because now we've taken into account the same shell electrons. So Z effective is equal to 16. So same Z, that hasn't changed. The only thing that's different is the way we calculated S, and that is 10.55. Okay, so we subtract, we get plus 5.45 as the effective nuclear charge using Slaters Rule. Okay, so it's very, very similar. It has just gone down a little bit from our rough estimate because we've taken into account that we do have screening that occurs in the same shield. Okay, so next we're going to do a 5s electron for strontium. Okay, so let's start off with our configuration. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, okay, 4p6, and now finally we'll have our strontium at 5s2. Okay, so when we do this, I want to reorder these because if you've noticed, we're doing this 100% by n value. So I want to reorder this because I have my n's out of order right now. So these are a little bit out of order right here. So I'm going to reorder this. So 1s2, 2s2, 2p6, 3s2, 3p6. Now, since this is n equals 3, I'm going to move it back. And I'm going to say 3d10. Now this I'm going to put with the other 4s. So 4s2, 4p6, and now 5s2. Okay. So this is our now configuration in sort of order of n value. Okay, so now we can kind of apply our rule. So we know everything here is going to screen 0.35. And the next end down, this one, these are going to screen at 0.85. And then everything else here is going to get the full screening value of 1. Okay, same shell, so n, same n minus 1, n minus 2, and below. Okay, so let's set up S. So S is going to equal, okay, so I like to start here. So a 5s electron, meaning there's only one other s electron. So 1 times 0.35. Okay, so now just one electron is screening at 0.35. Okay, so we have 6, 7, 8. All 8 of those are screening at the 0.85. Plus, now we have 10, 16, 17, 18, 19, 20, 26, 27, 28. So we have 28 electrons screening at a full 1 value there. Okay, so we're going to punch this into a calculator and see what this is. So I'm going to go grab my calculator and I'll be right back. All right, so now let's punch this into the calculator. Okay, so we have 1 times 0.35 plus 8 times 0.85 plus 28 times 1. So we get 35.15. Okay, so if we take a look, we have strontium is our element here, so it has Z of 38. So ZEFF equals 38 minus 35.15. Okay, so I'll subtract that, and we get plus 2.85 as the effective nuclear charge. So not feeling a plus 38, only really feeling something like a plus 2.85. Okay, so that is how Slater's rule works. Again, we're just putting into play here that we do have a slight screening in the same shell and increased screening as we move away from the shell that we're in. Okay, so I want to go back to our Prezi and look at some sort of calculations and measurements with Slater's rule and just using core electron screening. Okay. All right, so the green one here, the sort of green with the triangles, this is just using core electron screening. So sort of our real value here would be these advanced methods. So like computer modeling is what we have here. So this is going to closely approximate what we would see in sort of the reality of the situation is this blue line here. Okay, so the blue squares, kind of how things really work. And so the green line is just core electron screening here. So does kind of an okay-ish job when they're small, a much better job as the atoms get a little bit larger. Okay, so a nice sort of linear, steady increase as we move across the periodic table, just like we drew on our periodic table there. Okay. So next is Slater's rule. So that's the sort of yellow. So Slater's rule actually does a really pretty good job at approximating what's actually happening in nature. Okay, so again, using our Slater's rule does actually a really good job at predicting what actually happens as we move across periods with effective nuclear charge. Okay, so that's the difference. Slater's rule, a little bit more precise, taking into account same shell screening, but core electron is a really good sort of first approximation method. Okay. So next, I want to look at atomic radius. Okay, so atomic radius, how is this measured? Okay, so I want to go back here. I'm going to sort of brighten this up a little bit. Okay, so we are looking at what's called bonding atomic radii, or a bonding atomic radius. So this is a radius that is measured or approximated using a bond length. So what we do is we take some sort of bond. So the nucleus of the atom is the black dots, and this blue fuzzy, that's sort of the electron shell. So what we're looking at here is the bond length is the distance between the nuclei. So we can approximate, again, what the radius of an atom is by looking at the bond it forms here. So the easiest way to look at it is if it's what we call a homonuclear diatomic. So homonuclear means that this element and this element are the same. So for example, what we're going to do is I2. So this is an iodine and this is an iodine. So since they're the same atom, we can say the bond length here. If we take half of that, we should get the radius of one iodine atom. So that's exactly how this is calculated, and it's put into a table, which we're going to talk about in just a second. But this is essentially when we are looking at the atomic radii here, we're using the bond, and then again, the distance here. And if it's a homonuclear, if we take that and divide it by 2, we can get the radius of the atom. Okay, so let's do, I did a calculation, a couple calculations using iodine. Okay, so how is this measured? We saw that. So the first step is to measure our diatomics. So for example, I2. So the bond length of I2 is 2.66. So again, I2, the distance from nucleus to nucleus is 2.66. Okay, so that's what I have here, my terrible drawing. So if we were to calculate just the radius then of iodine, we would take that distance and we divide it by 2 because we know it has to be the same because this is an iodine and this is also an iodine. So they have to have the same bond length because they're the same atom. So if we take that and divide it by 2, we get 1.33. So that's our bond length or our bond radius for an iodine atom. Okay, so after we know that, we can use that in a what we call heteronuclear bond. Okay, so something like HI. So for HI, hydrogen is a lot smaller than iodine. So this one here is H, and this one here is I. Okay, so much, much smaller. So we can't just measure this and divide it by 2. So the bond length is 1.64. If we took 1.64 and just divided that by 2, we would get 0.82. Okay, so that doesn't match what we would have here. So that can't be correct. Okay, so what we're going to do is say, okay, I know this distance is the radius of hydrogen and the radius of iodine. Okay, so distance equals the radius of the hydrogen atom plus the radius of an iodine atom. Okay, so if I know that distance, that 1.64, from it, if I subtract iodine, which I know because I've already measured that, so if I subtract those, I should get the radius of my hydrogen. And that's exactly how it works. Okay, so since we've already measured iodine, we know essentially this distance for iodine as 1.33. So we know that the other part of this has to be hydrogen. So if we have our bond length, we subtract out the one we know for iodine, we can get hydrogen here. So that's how these particular things are measured. Okay, so we can use the bonding atomic radii to actually calculate or approximate the length of a bond. So for example, let's use the bonding atomic radii to predict the bond length of a oxygen-hydrogen bond. Okay, so that's where this table is going to be helpful. So we take a look at it. Okay, so if we look at what we have, so oxygen is here at 0.66. So we'll put that down. So we have 0.66 angstroms. And we're going to add to that the radius of the hydrogen, which is 0.31. 0.31 angstroms. So 6 plus 1 gives us 7, 6, 7, 8, 9. So we get 0.97 angstroms as the approximate bond length of an OH bond. So again, this was the radius of oxygen, and this was the radius of hydrogen that we add together that should give us the distance. So again, what we're saying, oxygen, hydrogen, that is our bond length, the distance between the two nuclei. We look this up in the table as 0.66, and we look this at the table as 0.31. Oops, sorry, my picture ran off there. So we add those together, we get the 0.97, which is our approximate bond length of an OH bond. And it's not entirely exact, but it's really, really close approximation. Okay, so let's see what we have next. So on the back, we're going to look at trends. Okay, so just like everything in this chapter, we're going to be looking at trends. So we want to figure out the left, right, and the up, down trend. All right, so let's go back to our diagram. Okay, so it's probably a little bit obvious what we have here. Okay, so these ones look pretty large. So if we're looking at left, right, the left side of the periodic table, those are a lot bigger than the right side. Okay, so increasing radius is going this way. Okay, so let's look at up, down. So helium appears to be much smaller than xenon, so we increase as we move down. So we can do that one here. Also increasing radius. Okay, so that's our trend, which we got from the plot, but the question is, of course, why? So I left big blanks here. So why would this atom over on this side that has less electrons have a larger radius than something over here? Like, for example, why would sodium have a larger radius than something else on this side, like chlorine? Okay, so the answer that we can explain for this one is it's all because of Zeff. So the answer is Zeff. So let's think about what that means. So we said over here on this side of the periodic table, effective nuclear charge is pretty low. Okay, so we're looking at stuff around like +1, +2, somewhere in there. Over here on this side of the periodic table, we're getting effective nuclear charges of like +6, +7, +8 up here. So because effective nuclear charge is a lot higher up here, the atom is attracting those electrons in much more effectively on this side, therefore decreasing the radius. Okay, so a larger Zeff on the right attracts the electrons stronger. And because, again, you have that stronger attraction, results in a smaller radius. Okay, so if you have a stronger force of attraction, it's pulling those electrons in tighter, you get a smaller radius. Okay, so that is effective nuclear charge. That's how we explain that one. Okay, so next was, how do we explain the up-down trend? How do you explain that this one has a much smaller radius than this down here? So this one we can explain with N. Okay, so this one probably makes sense as you're moving down the periodic table. So we're going from N equals 1, N equals 2, 3, 4, 5, 6, 7. As you're adding more electron shells, of course, that has to result in an increased radius. Okay, so addition of electron shells increases the radius. That one's not so bad. Pretty, I think, visual. You can kind of see how adding shells, we've drawn a handful of atoms this way, how adding those shells would result in a larger radius. Okay, so for this one, we want to place an order of increasing radius. So we have nitrogen, oxygen, phosphorus, germanium. So we're going to use the periodic table and follow our arrows. So we're going to follow our arrows. We're going to predict the order of smallest to largest, and then we're going to use that table of bonding atomic radii to see how we did for that. Okay, so let's grab our periodic table. So these are all, right here. We have nitrogen, phosphorus, oxygen, and germanium. Okay, so the first one they gave us in the problem was nitrogen, so we'll just sort of start there. Okay, so we want to compare nitrogen to oxygen. So we do know as we move this direction, so as we're going this way, that the radius decreases. So first note, we know that nitrogen should have a larger radius than oxygen. Okay, so I'm going to kind of put it in the center here. So oxygen is less than nitrogen. Okay, so we have, here we go. So we have our first relationship. So next, let's look at phosphorus. So phosphorus is here, so right below nitrogen. So I think we're going to want to directly compare nitrogen and phosphorus. So as we move down the periodic table, the radius increases. So phosphorus is larger than nitrogen. Okay, so we'll put our P right there. So we have N, we have O, P. So our last one is germanium. So that one is right here. So we can compare that one to probably phosphorus, but we could probably use any of them. Okay, so germanium is farther down, which indicates it should have a larger radius. And it's also farther to the left, which also tells us it should have a larger radius. So it's further this way, which means it's larger, and it's further down, which means it's larger. So our largest one here is germanium. So smallest oxygen, so we have O, N, P, and germanium, Ge. Okay, so let's see how that stacks up to what we have here. Okay, so we said oxygen was the smallest, so it is measuring in at 0.66. Slightly larger, nitrogen at 0.71. Okay, good so far. Phosphorus at 1.07, so good so far. Small, next. And then last, germanium at 1.20. Okay, so just following the arrows on the periodic table told us oxygen was smaller, next nitrogen, followed by phosphorus, and ending with germanium. So that's something that you would be expected to do again. So we'll put a check mark there. They did match what we saw on the table. So you should be able to use a periodic table and follow your arrows, knowing again on which side of the periodic table you have large atoms, which side you have small, and again directly compare based on their location on the periodic table. Okay, so that is that for now. So this concludes lecture number 2 for chapter 7.